finish up 4.1 here. We're going to review all the remaining exercises here. So let's take a look at number 7. What we're going to do is create the equation to this polynomial function. You can see the graphs are given below. And all you got to really do is take a look at the important values that they give you. For example, this graph here, they give you that there's a root at -3, a root at -1, and a root at 2. So what I'm going to do is I'm going to build a basic equation with those roots. I see that at -3, because x equals -3, that's stemming from a factor of saying x plus 3. Since it's passing through the graph, I know that this is a degree of 1. I'm going to multiply that by the next root, and so since our next root is at -1, I'm going to go ahead and say that the step that came right before x equals -1, that was x plus 1. So our next factor rather, will be x plus 1. Since the graph rebounds off, we know that it has a degree of 2, a multiplicity of 2. So I'm going to go ahead and put a 2 there. From there, we have our last root at x equals 2. And so since x equals 2, that must mean that its factor is x minus 2. And we again see the graph passes through, so that's a degree of 1 again. Now this graph can change depending on how the graph may be transformed. But if you have the zeros at these points, which I've denoted with the purple dots, technically we could stretch our graph out. We can maybe elongate it, right? And if you stretch the graph out like so, what you'll notice is that it has the same zeros, but the graph ended up just getting stretched vertically. And when you stretch the graph vertically, what you're basically saying is that, oops, I'm sorry. Let's go back. What you're basically saying is that you're multiplying the function by some vertical stretch or shrink. So that's times the a value. And so what we're going to do is solve for that a value now. So one thing that you'll notice on the graph is you want to look for a particular point. Every one of these points are kind of hard to tell what they are, other than the zeros. These points are kind of hard to say like where they are, right? There's not exactly a nice point. The only nice point that does exist is right here. And I would call this the point 0, -3, or that's basically our y-intercept. So we're actually going to plug that point into our function and solve for a. So -3 represents the y value, and we'll solve for a, and x represents the 0. So we'll say 0 plus 3 times 0 plus 1 squared times 0 minus 2. And essentially what we're doing here is we're solving for a. So if we go ahead and divide both sides by 3, you get -1 equals a times 1 squared times -2. The 1 squared just becomes 1, right? And then we just divide by -2. So we see that a is actually equal to 1/2. So we put that back into our function, and we're going to get 1/2 times x plus 3 times x plus 1 squared times x minus 2. And that's going to be the equation of our graph over here to the left. Okay, so let's apply that same technique for the second graph here. For the second graph, again, we look for the zeros. Those are the important parts, right here and here. So we definitely see that there's a 0 at 0 itself and a 0 at 1. So we know that in its basic form, with some kind of vertical stretch, you might say that the 0 is at x, because that would be x minus 0. And then the other factor would be x minus 1 because of the factor at 1. So now what we can do is, again, plug in a point we know. We definitely know that there's this point 2, -4 that exists. So I'm going to plug in -4 for my y value, since that represents y. And I'm going to plug 2 in for my x value, since that is x in our ordered pair. So I'm going to go ahead and say -4 is equal to a times 2 times, and then the x value again being 2, so 2 minus 1. When we solve this, we'll see that 2 minus 1 just gives us 1. Divide both sides by 2, and you can see that a is -2. So in its final form, we can see that the function has an a value of -2. You still have an x to represent the 0, times x minus 1 is your other 0, and that'll be your equation there. Oh, I'm sorry. I forgot that the 1 was a double root, and so that double root means that we should have a squared there. Now, if you take a look at the final function, now it turned into x to the third power, and not only that, but our leading coefficient is negative, and so therefore we know that the graph should be going up to down, and it should look like a cubic, which it does. So now I know that my answer is correct. Okay, let's go on to number 8 here. Let's take a look at this. This is like what we did in class as well. Basically what you want to do is you want to look at your zeros here. Your zeros in this case would be x equals -4, x equals -1, and x equals 2. In terms of those roots, what we can also discuss is this multiplicity. And I'm just going to go ahead and write these down below because it just seems to make sense to put it together. So we see that -4 has a multiplicity of 2 since we see a degree of 2. The x plus 1 has a multiplicity of 1, and x minus 2 has a multiplicity of 1 as well. So that way we know that -4 at least is a double root, 1 is a single root, and 2 is a single root. And I think it's just dawned on me that I'm putting my work in the wrong spot. All this should actually be down here, the zeros, and its multiplicity. All right, so aside from that, what we also need is to discuss its end behavior, and its end behavior is determined by the a value. You'll notice that if you actually multiply all these numbers together, x times x times x times x, that's basically a big ol' x to the 4th power, and you'll notice that it has a leading coefficient of 1, so the a value is 1, or more precisely, it is a positive 1. And then because we see it's x to the 4th, we know that the total degree is 4, which means that we know as an even function being positive, our end behavior should be going something like up to up, basically, something along those lines. Okay, so now we're going to go ahead and graph this. So on our coordinate plane here, I'm going to go ahead and make some marks here. And just because of the numbers that I see here, I'm going to go ahead and make it so that every 2 marks represents a length of 1. And that'll just make it a little bit easier to see our graphs. It'll be a little bit more zoomed in. So there we go. Okay, let's see if we can get by with that. Okay, so we know that the zeros are at -4. I'm going to go ahead and put a dot there. We also have -1, put another 0 there, and also at 2, put another 0 there. In terms of end behavior, we talked about how it's going up to up. So we should be starting from quadrant 2, somewhere up here. We're going to make our way through -4. Now at -4, keep in mind that it is a double root, so you do want to bounce at -4. So what I'm going to do is I'm going to go ahead and start at -4, show my bounce as it goes up like that. And since I know it's going to bounce, I'm going to go ahead and draw it the other way as well, kind of like this. So that way it bounces up like that. And then I'm going to go ahead and take a look at how my graph will interact with the next 0. I notice that at -1 is a single root, so I should be passing through this location here. So I want to make sure that my graph is going through. Okay, so what I'm going to do is I'm just going to make this graph go back down, and it's going to pass through -1 just like so. You'll notice how that graph is nice and smooth and continuous. Now, as we go through, here's going to be a tricky part, actually, and you'll want to pay attention to this part especially. I'm going to zoom in. Oh, I guess I can't zoom in too much. I'm going to zoom in just enough so you can see the coordinate plane. Now I'm going to change a different color here so you can really see what's going on. Basically, you'll see that from -1 to 0, that's a distance of 1, and then this is a distance of 1, and then another distance of 1. So that's a total distance of 3. Now, what I see a lot of students do is they make a common mistake of saying that just because this is the y-axis, they think that this is really important, and they want the y-axis to also represent the minimum value of a graph, or even the maximum value of a graph. This is not the case. When you actually look at the graph, you'll notice how the graph has less distance on the left side and more distance on the right side. So if you were to actually graph this symmetrically, and you would just want to make the graph go nice and smooth, what you'll notice is the graph will go down, and it will keep going down, right? But then it'll go down a little bit further, and then finally kind of come back up so that it can go to that value of 2, which is, again, another single root. So we're going to go up through and then pass through 2, just like that. So you'll notice what I did in my graph is actually the y intercept is not actually the minimum value. My minimum value is kind of like more like midway in between my 2 zeros, because what goes down must come up, and you want to make sure that it flows very smoothly and it's not just a sudden twist and turn. Okay, so you want to make sure that you're doing that in your graph as well. All right, so that's that graph there. Again, we don't exactly need to know the y-intercept. Actually, we could find it. If we say that the x value is 0, you can see how the 4 squared will give you 16, and then you'll multiply that by 1, and then you'll multiply that by -2. So the y-intercept is actually -32. Now that number is really large. So because of that, you don't really need to label it so precisely. Like, you don't need to be graphing all the way down here at -32, but just know that the y-intercept is intersecting at -32. That's all. Okay, so you can see that the scale on the x-axis is not exactly the same as the scale on the y-axis. All right, let's go on to our last graph here. So letter B here. Again, I'm just going to label the things. I notice that with x squared, that's telling me that it has a 0 at 0. And I also know that it has a multiplicity of 2, telling me it's a double root, it'll rebound. At x minus 3, I know that my 0 is 3. And again, the degree is 1, so therefore it's a multiplicity of 1. And I know it just passes through. X plus 4, same scenario. I just see that x equals -4. It's still a multiplicity of 1, and therefore, again, the graph just passes through. In terms of the actual leading coefficient, what we notice here is that we're multiplying x squared times x times x. That'll give us a total x to the 4th power. So we know that we're dealing with a 4th degree polynomial. In addition to that, there is a negative leading coefficient, and therefore a negative x to the 4th will give us an end behavior that is down to down. So now we know that our graph is going to start in quadrant 3 and it's going to make its way over to quadrant 4 as well. Okay, so let's go ahead and make it more exact. Based on my zeros again, I'm going to go ahead and label my axes. Don't forget to always label your axes, and I'm going to label it again every 2 units as a length of 1, just so everything is nice and spaced out. And let's begin graphing. Alright, so we see that at x equals -4, there's a 0. At x equals 3, there's a 0. And x equals 0, there's a 0. Okay? Alright, so let's go ahead and graph this. Again, we know that based on the end behavior, we're going down to down. So we start at quadrant 3. We're going to go through -4. Keep in mind that -4 is a single root. Therefore, it's going to pass through -4. And so I'm just going to go ahead and draw that in. Just like that. Okay? And then we need to make our way back to 0. Now keep in mind at 0, 0 is technically a double root. And so for that reason, we're going to rebound off 0. Again, notice how I'm kind of like around like the, -2, -3 area. So by the time I reach -2, and I've reached my max, and I'm going to come back down, rebound off 2, and then I will come back up, right? And as I come back up, let's take a look at what's going on here. I need to make my way back to 3, and I need to pass through 3 because it's a single root. Very similar to what I said in the previous example, you'll notice that this is a distance of 4 versus this being a distance of 3. So because the left side of the graph had a lot longer to travel, it had a longer time going up and then coming back down. So basically what I'm saying is that this part of the curve, it is going to look a little bit more stretched out. Versus the right side of the graph, because it only has a distance of 3, it doesn't require so much time to go up before it makes its way back down. So what we will see is that actually this graph, this graph will have a higher value of y's on the left side compared to the right side. So I'm going to go ahead and make my graph go up, but it won't be able to, it doesn't have as long to go up. So therefore, I'm just going to stop it right around there and make my graph go back down like that. So you'll notice in terms of height, the left side is going to be higher than the right side, simply because it has more distance to cover in the span from -4 to 0, as opposed to over here, you're going from 0 to 3. Okay, and that'll do it for this lesson.